If you solve the coefficients, so C1 already we got. C1 is going to be G of 0. Now, if you consider these two terms, if you add these two will go, and you know C1, from this you can find C3. Knowing C1 and C3, I can find C2. That is what is done here. See here. So this is mathematical. I am not deriving. You can do it by yourself. It is very simple. So in C1 is G of 0, C2 is G of V minus G of minus V by 4V, and C3 is G of V plus G of minus V minus 2 G of 0 by 6V square. And substituting in the IP3 expression, you know the expression for IP3 we have derived for 2 by 3, C1 by C3, 1 by RS. C1 I know, C3 I know. I can substitute C1 by C3 into 1 by RS. So I'll get the expression here. This is the expression for IP3. Very simple 3-point method. I am assuming that the output current will vary just like this function G of V. Okay, because I cannot directly measure this value. I cannot directly measure from only one equation. I need to have another mapping where I will superimpose this function I on G. And I am substituting the three boundary conditions 0, V, and minus V. That I'm going to use that as the boundary condition for finding out the coefficient C1, C2, C3. So once knowing C1 and C3, I can find IP3 using the formula, what we have derived. This is one accurate method of determining, estimating IP3 in hand. Having the coefficient C1 and C3, I can find IP3 using this formula. This is very much faster compared to any simulation software, whatever we are going to use. And this is also found to be very accurate. For any design point of view, this value of IP3, whatever you get from the 3-point method, is used as a standard for designing the amplifier for your high frequency applications. And the IP3 is typically about 10 to 15 dB beyond the 1 dB compression point. Whatever, if you are calculating using the above formula, they found that first the 1 dB compression point comes. After 10 to 15 dB only, your IP3 point is going to come for your amplifier. Because the amplifier is going to slowly fall off from the 1 dB compression point to your IIP3 product. Now, having known what is the IIP3 point, now our goal is to decide what is the expression for SFDR. So, you know, SFDR is it is going to be the difference in power. The upper bound is going to be the peak power of your signal, whatever you are going to send, and the lower bound is going to be the noise. Okay, so having known the definition of SFDR, I can easily relate IIP3 with SFDR, and I can find the mathematical formula for SFDR. Okay. So in the context of LNAs, we have said again that third order products play a major role in spoiling the performance. So SFDR is a very popular term to quantify the performance of your LNA. So it is more or less like your SNR of your system. So how you say that if SNR is very high, the system is very good. Same way, if SFDR is very good, SFDR is very high, we can clearly say the system is going to perform well under noisy environments also. So as the input amplitude increases from 0, the first order output initially has a negative SNR, but eventually it emerges from the noise floor. So initially when the input amplitude and noise level are same, then the SNR is going to be very minimal because the input signal and noise level are same. So the SNR is almost 0. But as the input signal increases from 0, SNR will become very much positive and it will come out of the noise range and SNR will become positive. So that is what